Internal loading developed in structural members. Now, as engineers, mechanical as well as civil, it's very important that when we're designing structures that it doesn't exceed the operating limit. So it's very important to be able to understand what's happening within the material, these internal loading. So consider a beam. Let's say it's adhered to a wall, and there's a force of F2 applied at, let's say, point C, force of, let's say, F1 applied at point B, and let's say this is called point A. What we want to know is the internal loading that's developed in this particular beam. So we'll take it step by step. Let's draw the free body diagram of this beam when it's freed from its wall support. So we have to draw the external forces, F2, F1. At the wall, we know that the wall prevents the beam from translating in the X and Y directions. Therefore, we'll have reaction forces in those directions. So we'll call this AY and AX. And I'm just guessing the directions of those reaction forces. The beam from having... The wall also prevents the beam from rotating. Therefore, we'll have a reaction moment. And I'm just going to assume that it's in the counterclockwise direction. So that's my free body diagram. Now let's take a look at this point, let's say point P. And I want to know what are the forces and moments within that member at point P. So in order to do that, we need to section it. Once I section it, I have two beams or two parts of a beam. So here's the one part that's from A to P, and here's the other part from P to C. So I'll label this point as P. This label is also, that point's also P. At C, I have force 2. At B, I have force 1. And at A, I have the same forces as before. So AX, AY, and a moment. So these are free body diagrams. I'll call this FBD number 1. I'll call this FBD number 2. Since these are a free body diagram and I'm making an assumption that these members are in equilibrium, then if I were to apply the equations of equilibrium on this portion of this beam, the equations of equilibrium must be satisfied. Well, if that's the case, then if I have AX going that way, then I must have another force going to the right to balance that. So I'll call that PX. If I have a force going upwards, then I definitely have to have a force going downwards. So I'll call this PY. And I have this bending moment going this way. The sum of the moment must equal to 0, so I must have a reaction moment going in that direction. MP, well, point P on this portion of the beam is the same as this point P on the right portion. Therefore, I have to have the same forces on this side. So equal and opposite. Equal and opposite of PY going down would be force going up. Equal and opposite to this moment in the clockwise direction must be equal and opposite to this moment P. So here we have two free body diagrams that resulted from one beam. So now what we have to do is talk about sign conventions. So I know so far in our analysis, we said that if we establish our X, Y, Z axes like that, if the force is going in these positive X, Y, Z direction, we said it would be positive. And in terms of its moment, if we use a right-hand rule and our thumb points in this direction, we said that would be positive. That is still true, but now what we're going to do is formulate another sign convention to talk about these internal loadings. Another sign convention for internal loadings. So let's take a look at this member right here. Let me first cover the nomenclature for internal loading. That Py force up there acts on the face of this beam. Therefore, we call that a shear force. That Px force acts on the area, the cross-sectional area of that beam. Therefore, it's customary to call that Px a normal force. And when we talk about these internal loading, this shear force will be considered positive if it causes this shear force will be considered positive if the member that the shear force is acting on rotates in a clockwise fashion. So if this Py is acting upwards on this face, of course it'll cause this beam to rotate clockwise. Therefore, this is considered positive. Let's look at this face. We have this Py force acting on this face of the beam, which causes this beam to have a tendency to rotate in the clockwise direction. Therefore, that shear force Py is considered to be positive. Let's go on to the normal force. The normal force will be considered positive if it causes a tension on the beam that it acts upon. So Px pulls on this beam, therefore this member would be in tension, so we'll consider that to be positive. So positive if clockwise rotation, normal force positive if tension, if the member is in tension. The moment at P. Now let's move on to the moment. So we look at this moment MP, and that causes this beam to actually bend in a convex shape. So if it does that, then it'll be considered to be a negative. So that would be a negative moment up there. So negative if it causes a convex bend. Suppose we had a member, the reaction moment turned out to be this way. It'd be clockwise. So we'll call that M sub some other variable, let's call it Q. Well, this moment causes this beam to bend in a concave manner. Therefore, this will be considered a positive moment. And again, this is just to signify whether the internal loadings are positive or negative. If we're applying the equations of equilibrium, then you use this sign convention, meaning this is a positive force, this is a negative force. This is a positive x force, this is a negative x force. This is a negative moment, MP. This is a positive moment, MP. However, if I'm trying to communicate with you and I want to describe those forces at this internal section, I'll say on member 2, we'll call this member 2 and we'll call this member 1. So I'll say on member 2, there is a positive shear force and a positive normal force with a negative moment. If I'm talking to you about member number 1, then I'll say that the internal loadings at P has a positive normal force, a positive shear force, and a negative moment. It's a little confusing, but I want you to know this sign convention will come into play when we start drawing our shear moment diagram. And this will come up in the next section. For now, whenever you apply your equations of equilibrium, you always want to use this sign convention. Don't pay attention to that when you're doing your equations of equilibrium. So in this diagram, I know that since there's a shear force By going in that direction, I need an equal and opposite force going in that direction. So that would be By. And again, I'm going to draw this normal force, call that Bx, and we know it's equal to 0. And I'm also going to draw a moment that's equal and opposite to this, and say that's also equal to 0. So I look at this system right here, By, moment, and a normal. So it'll balance out. So these are the free body diagrams once I section it at B. I could also section it at, let's call it just to the right of the 6 kilonewton. Let's call that section B, and let's call this point C. So if I were to draw the free body diagram after it's been sectioned at BB, I would get this. So I have my reaction force due to the rocker. I have the 6 kilonewton force is now on this member. So 6 kilonewton. And I'm going to draw my shear force, which would be Cy, my normal force, Cx, and my moment at C. And I know that's equal to 0 because if I were to do a free body diagram analysis of this segment, there's only one moment vector on this diagram, therefore sum of the moment must equal to 0, so it's equal to 0. And the reaction moment on this member would be equal and opposite to this, and equal and opposite to that moment. We would have to apply this external 9 kilonewton force, that 9 kilonewton, we would have to apply that 9 kilonewton meter moment here, along with the reactions at dy and dx. So as you can see, for a given member, if I had wanted to know the internal loading at point B, I section it at B. and I draw the free body diagram, and I apply the equations of motion. I apply the equations of equilibrium. If I had wanted to know the loading at C, that's where I would section it, and then I would get this scenario where, again, apply the equations of equilibrium on this member or even on this member, and we should be able to determine the internal loading at that section.